Alright, so last video we talked about what a centroid was, sort of. I didn't cover it in its entirety. Instead, I showed you guys a table, this table right here. I'll flash it up on the screen for just a little bit. And this is what we use to go ahead and calculate basically the equivalent point force load that represents a distributed load. Because again, we can represent any distributed load as a point force load at the centroid of the distributed load. And that made our life a lot easier when it came time to solving distributed load problems, because it's quite simple to solve a point force load problem, and it's quite simple to solve for moments when they act at specific points instead of every single point on the body. And later on we're going to get into shear and bending moment diagrams, which are going to rely heavily on these concepts that we've talked about. But I wanted to take a little bit of time today to go ahead and walk you guys through the process that I went through for calculating the center of gravity for the plane. As you guys all know, the center of gravity is an incredibly important concept, and it's really important to have a really good approximation for that during design phase. Because if that center of gravity is too far to the rear of the plane, we're going to constantly run the risk of stalling during flight. And if the center of gravity is too far forward, I mean we're constantly diving, which is indeed preferable to stalling, but it's still an issue. We want the center of gravity to fall at a very specific point on the plane, and in order to do that, we have to apply all of the tools that we've talked about so far. I'll walk you guys through it today on how exactly the center of gravity for the DBF 2020 plane was calculated. So I'm not going to do every single calculation because it took me about 8 hours by hand to actually walk through the entirety of it, because I literally took account for every single mass on the plane. Instead of doing that, let's go ahead and simplify it, because the concept is the same. You can always add extra complications and extra pieces, but the way to calculate it is essentially the same. Now, I'm not going to actually write down the equation for center of mass. I'll do that at the end. And the reason for doing that is I want you guys to understand where this concept comes from. Because if you understand where it comes from, you can derive it any time. So let's go ahead and let's draw a plane, roughly. Okay, this is a rough picture of the plane, very rough. So I've included the nose, the batteries, the fuselage, the empennage, the tail, and the wing. And this is a very rough simplification, but again, the concept is the same. Now, what I'm going to do is I'm going to define my axes. I'm going to define my y-axis as going up. I'm going to define my x-axis as going this way, with the origin at the very tip of the nose. Okay. Now, our plane was roughly, I want to say 46, if I recall correctly, 46 inches long. So let's say that the back of the tail is all the way at 46 inches. Okay. Now, when calculating the center of gravity, you have to do it in two ways. You have to calculate the y center of gravity and the x center of gravity. I'm just going to do the x because the y, it's the same thing, but in the y direction. And again, all the things we've talked about with the summation of forces, they all apply here. Because I can take each one of these sections. Now, this entire geometry, this distribution, I might not know how it works. But if I decompose it into a bunch of these small sections, and then solve for the weight force of that small section at its centroidal location, like we did last video, I can express all of these different pieces of the body as point forces at a specific location, right? Because again, any distributed load, and if you think about it, a fuselage is nothing more than a distributed load. We basically have a fuselage where it's a constant load per unit length, right? Because the ribbing is more or less evenly spaced. The skin is distributed evenly. So if I go ahead and I approximate that as a rectangular load, that's not a bad assumption, right? For the empennage, because we have that taper from the side profile, it's awfully similar to a triangle. I can approximate that as a triangular load, right? Etc., etc. Now, I know the plane actually didn't look like a triangle in the empennage. In fact, it looked more like that. But again, you can do that as well. Just break it down into more pieces. I'm simply going to simplify everything that we've done and show you guys the method. And hopefully by showing you the method, you can do this calculation on your own. So let's go ahead and make a couple of, let's just have a couple of numbers here. Let's say, for example, that the battery here, that this battery has a weight of, what was it? It was roughly about 3.5 pounds. Okay, and that's going to be a distance of roughly 7 inches back. The nose, roughly 5 inches back. And I believe it had a load of, I don't know, let's call it 0.75 of a pound. The wing came out to be roughly like 4 pounds with the motors included in the ESCs. And that was roughly here. Let's call that at like, I want to say 14 inches. Actually, with the motors, it's going to shift it forward. Let's call it at 12. The fuselage fell about here. In the center, again, rectangular load. Was pretty light. Let's call that, let's call it 1 for the sake of it, 1 pound. Empennage, again, triangle rules. It would fall 1/3 from that front edge. Empennage is pretty light. Let's call that at 1/2 pound. It's probably less than 1/2 pound. I believe this is at a distance of like roughly 19. This is at a distance of roughly like 26. And I believe this back section of the tail here, again, the center would be here 1/3 from that side. That's at a distance of roughly 2 inches from 46-ish. We'll call it 43. And the tail ended up being about 0.75 pounds. So I've just gone ahead and sketched out really rough approximations for center of mass and loads and everything for the plane. I obviously haven't accounted for everything, but again, the method is the same. So what I can do now is I can basically, of course, to get the total weight of the plane, I can simply equate all of these loads, which I'll do right now. 0.75, 3.5, 1.0, 0.5, that was 4, 4.0, hopefully I'm not missing any there. 1, 2, 3, 4, 5, 6, 7. Sure, and we can go ahead and sum this. 5, 2, 6, 10. Okay, if we sum it, 11 pounds. It's pretty decent. That's pretty close to what the plane was. So we have a total force downward of 11 pounds. Now, what we can do here is we can do basically a summation of moments about a reference point. In this case, I'm going to take the 0 point, that 0 axis, a 0 on my x, to be my reference point. And if I go ahead and calculate an equivalent moment given the distance from this point, which we've already established, I can set that equal to the total weight at a certain distance. And essentially what I'm doing is I'm solving for the centroid of the entire body, right? Because I'm going to take the total mass and apply all of these distributed loads, all of these point force loads. I'm going to apply all of that at a specific location, which is then going to be equal to the summation of all of them. So it's a really tedious calculation, but it's not very difficult to set up in concept. Because when you're looking at your design, you essentially know the distances of every single mass on the plane. It got to the point where I was literally putting in these 12-gram servos and calculating the effect of that 12-gram servo at a specific distance. So you can always take this a step further, but the concept is the same. So let's go ahead and write out that equation. Let me erase this. Okay, so what I'm saying is that the centroidal distance of the entire body, so let's call that CT, just for the heck of it, multiplied by 11, right? Because the total weight is 11 pounds, is going to be equal to, and here comes the fun part, 0.75. Okay. Now I think I did that correctly. Anyway, now if we go ahead and we solve this, and I'm going to have to use a calculator, so give me a quick second. But if we go ahead and we solve all of this out, we're going to get basically a net sum which is equal to all of the distributed moments. And if we go ahead and we already have that set equal to CT times 11, we simply divide by 11, we'll figure out what the centroidal distance from the neutral point that we've chosen is going to be. One second. Okay, now I might have made a mistake along the way, but again, the concept is the same. It's a bit messy up here on the board. I'm going to say that's equal to roughly 140.5. You guys go ahead and do the calculation and let me know if I made a mistake. 140.5 divided by 11 is going to give me a centroidal distance of 12.77. All right. So that is the center of gravity for this body, roughly, which is going to fall, if I've defined this distance here as being 12, slightly behind that, right about there, on the plane. And as you can see, it's not that bad of a calculation. It's just very tedious, and it requires you to take a lot of different masses at very specific distances and make sure that you do your summation properly. I did it by hand. It's probably easier to do it in the computer. But again, as long as you're very diligent about how you're taking the calculation, this here is a very easy way to calculate the center of gravity. So I hope that was pretty informative. I might have made a mistake somewhere. It got a little messy. But again, the concept is the same. You can go ahead and solve for the center of gravity by taking a summation of the moments about a neutral point and setting that equal to the total weight times the centroidal distance. So before we leave, let's go ahead and concretely write out what the center of gravity calculation actually is. And it's essentially what we've just talked about. Okay, so generically speaking, if we write this equation out, what we're saying is M1. Now, what we're going to do is we're going to pull G out because, again, the weight force in pounds has a gravity piece inherent to it. But you can simply do this with mass because that gravity acted on everything, so we could pull it out and just work with mass. So mass 1 multiplied by the distance 1 that it is from the neutral axis plus m2 d2 dot 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 all the way to m n dn. Okay? You add this all up and simply divide by m1 plus m2 dot 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 plus m to the n, okay? And that's going to be equal to your just call it x, centroidal distance. And again, this should make sense because each one of these is a moment, m1 d1 is a moment, m2 d2 is a moment. So it's a summation of moments divided by the total mass, right? If I were to move this to this side, I'd have total mass times centroidal distance is equal to a summation of moments, which is exactly what we just did. So, of course, this equation gets very long, it gets very ugly as you add in every single possible massed element on the plane. But at its heart, it's quite simple. Summation of moments divided by total mass is equal to your centroidal distance. So hopefully that made some sense. And now all of you guys are perfectly capable of calculating center of gravity for DBF plane 2021. So thanks for watching. I'll see you next video.